are going to study the coordination compounds. Now you must be wondering, why should we study coordination compounds? Actually, many important components of everyday products such as cleaning materials, medicines, inks and paints include coordination compounds. Coordination compounds are found in many places on Earth's surface. Every living system includes many coordination compounds. Hence, it is necessary to study the chemistry of coordination compounds. To study the chemistry of coordination compounds, today we will study difference between a double salt and a complex, coordinate bond, definition of coordination compounds or complexes, Werner's coordination theory and interpretation of experimental data by Werner. Sometimes coordination compounds are confused with double salts. So, let us understand the difference between coordination compounds and double salts first. Both the double salts as well as complexes are formed by the combination of two or more stable compounds in stoichiometric ratio. They differ in the fact that the double salts such as carnallite means potassium chloride, magnesium chloride 6H2O or Mohr salt, ferrous sulphate, ammonium sulphate 6H2O, or we can say potash alum whose formula is potassium sulphate, aluminum sulphate 12H2O etc. dissociate into simple ions completely when dissolved in water. However, complex ions such as FeCN6 4- of K4 FeCN6 do not dissociate into Fe2+ and Cn- ions. Or we can say that if we dissolve K4 FeCN6 in water, it will not give the test of Fe2+ and Cn- ions. Now you will not get confused between coordinate compounds and double salts. To understand coordination compounds, it is necessary to have an idea of coordinate bond. Coordinate bond is similar to covalent bond with some differences. As you know that a base makes available an electron pair and an acid accepts an electron pair to form a coordinate covalent bond. Such bonds are often represented by arrows that point from the electron pair donor, that is Lewis base, to the acceptor, which is known as Lewis acid. Here you can see that in ammonia molecule, nitrogen has a lone pair of electrons, and in boron trichloride molecule, boron is deficient of electrons, that is, its octet is not completed. Hence, nitrogen can donate its lone pair of electron to boron to form a coordinate bond. Here the coordinate bond has been shown by the arrow from the donor side to the acceptor side. The chloride ion acts as Lewis base because it can donate its lone pair of electrons to tin tetrachloride. Here the octet of tin is completed, but as you know that tin has empty d orbitals, hence it can expand its octet, or we can say that the lone pair of electrons from the chloride can be accommodated in empty d orbitals of tin. Hence, two coordinate bonds are formed from chloride to tin. The red arrows represent coordinate covalent bonds. These arrows do not imply that two tin chlorine bonds are different from the others. Once formed, all the 10 chlorine bonds in SnCl6 2 minus ion are alike. Now you are able to define coordinate bond. As coordination compounds or complexes contain coordinate bond, hence it will be easier for you to understand what are coordination compounds or complexes. Most of the d transition metal ions have vacant d orbitals that can accept electron pairs. Many act as Lewis acids by forming coordinate covalent bonds in coordination compounds, or we can say in complexes. Here you can see the ground state electronic configuration of D series transition metal ions. For scandium, it is 4s2 3d1. Similarly, for titanium and vanadium, it is 4s2 3d2 and 4s2 3d3 respectively. But you can see here that for atomic number 24 for chromium, the electronic configuration is somewhat different. It is not 4s2 3d4, but it is 4s1 3d5. Similarly, you can see that the electronic configuration for copper with atomic number 29 is also somewhat abnormal. 3d subshell is filled before filling 4s. The electronic configuration of copper is not 4s2 3d9, but it is 4s1 3d10. Other electronic configurations in this D series are normal, but you must note that chromium and copper show abnormal behavior in their electronic configuration. Now, complexes of transition metal ions or molecules include cationic species like CrH2O6 3 plus or AgNH3 whole twice 1 plus, or they can include anionic species like nickel CN4 2 minus and MnCl5 3 minus. They can also include neutral species like FeCO whole 5 and PtNH3 whole twice Cl2. In this table, you can have a look on some coordination compounds with Lewis base, Lewis acid, donor atom and coordination number. If we see AgNH3 whole twice plus 1, here ammonia molecule acts as Lewis base and silver acts as Lewis acid. Now, donor atom in ammonia molecule is nitrogen and coordination number here is 2. In zinc CN4 2 minus, Cn acts as Lewis base, hence it donates its electron pairs. Zinc acts as Lewis acid and carbon atom of Cn acts as donor atom with coordination number 4. In NiCN4 2 minus, Cn again is Lewis base, nickel is Lewis acid, carbon atom is the donor atom with coordination number 4. Similarly, in PtCl6 2 minus, chlorine donates its electron pairs, platinum accepts the electron pair, chlorine is the donor atom with coordination number 6, and in NiNH3 whole 6 2 plus, again the ammonia molecule acts as Lewis base and nickel acts as Lewis acid. nitrogen is the donor atom and coordination number is 6. Now we will proceed to most important theory of coordination compounds known as Werner's coordination theory. Bonding in transition metal complexes was not understood until the pioneering research of Alfred Werner, a Swiss chemist who received the Nobel Prize in Chemistry in 1913. Now, prior to Werner's work, the formula of transition metal complexes was written with dots. For example, CrCl3 dot 6H2O or AgCl dot 2NH3. Just like double salts such as ferrous ammonium sulphate hexahydrate, which is written as FeSO4 dot NH4 2SO4 dot 6H2O. As you know that the properties of solutions of double salts are the properties expected for solutions made by mixing the individual salts. However, a solution of AgCl2 ammonia or more properly AgNH3 whole twice Cl behaves differently from either a solution of silver chloride or a solution of ammonia. The dots have been called the dots of ignorance because they signified that the mode of bonding was unknown. In 1893, Alfred Werner proposed a theory to explain the existence of complexes such as COCl3 dot 6NH3, COCl3 dot 4NH3, PtCl2 dot 2NH3 and FeCN thrice dot 3KCN. He began by assuming that a metal ion has two kinds of valencies. The first, the primary valency, which is ionizable and it corresponds to the oxidation state, and the ionizable valency is satisfied by negative groups that balance the charge on the metal. For example, in COCl3 6NH3, the 3 valency of cobalt is satisfied by 3 Cl minus ions. Secondary valency is non-ionizable and it corresponds to the coordination number. And secondary valency is satisfied by neutral or anionic species. And every element usually satisfy both its primary and secondary valency. Further, he recognized and proposed that these secondary valencies would be distributed around the metal in fixed positions in space in such a way so as to lead to the least repulsion between the groups or atoms attached. A secondary valency is used to bind other groups that are usually specific in number. In this figure, we have shown primary valencies with dotted lines and secondary valencies with bold lines. And in a complex like COCl3 5 ammonia, the coordination number of 6 for cobalt is met by 5 ammonia molecules and 1 Cl minus ion being bonded directly to the cobalt. Here you can see Cl minus ion is bonded with secondary valency. This leaves 2 Cl minus ions that satisfy part of the primary valency, but these are not bonded directly to the cobalt ion by means of a secondary valency. Hence, the formula for this coordination compound is written as COCl NH3 whole 5 Cl2. Similarly, for the complex COCl3 6 ammonia, the 6 ammonia molecules satisfy the secondary valency. You can see here 6 ammonia molecules are bonded with bold lines, means these 6 ammonia molecules satisfy secondary valency and 3 Cl minus ions satisfy primary valency, and the formula for the complex can be written as CO NH3 whole 6 Cl3. Similarly, for a complex COCl3 4NH3, the coordination number of 6 for cobalt is met by the 4 ammonia molecules and 2 Cl minus ions being bonded directly to the cobalt. That leaves 1 Cl minus ion that satisfies part of the primary valency, but it is not bonded directly to the cobalt ion by means of a secondary valency. Hence, the formula of the complex can be written as CO Cl2 NH3 whole 4 Cl. The electrical conductivity or conductance of solutions containing the complexes provides additional confirmation of the correctness of Werner's view. So, let us define conductance of a solution. The conductance of a solution of an electrolyte is a measure of its ability to conduct electricity. It is related to the number of ions and the charges on ions in solution. For example, when COCl3 NH3 whole thrice is dissolved in water, the compound behaves as a non-electrolyte. There are no ions present because the Cl minus ions are part of the coordinate sphere. Support for these ideas is provided by dissolving the compounds in water and adding a solution containing silver plus. In the case of COCl3 6 ammonia, or we can say CONH3 whole 6 Cl3, all the chloride is immediately precipitated as silver chloride. Similarly, for COCl3 4NH3 or COCl2 NH3 whole 4 Cl, only 1/3 of the chloride precipitates as silver chloride, because 2 chloride ions are bound to the cobalt ion by coordinate bonds, that is, they satisfy the secondary valency. 2 chloride ions satisfy both primary and secondary valencies of cobalt, but 1 Cl minus ion satisfy only primary valency. Now, for a solution of the compound COCl3 NH3, none of the chloride ions precipitate when silver is added, because all of them, that is, all the 3 Cl minus ions are bound to the cobalt ion by coordinate bonds. On the other hand, CONH3 whole 6 Cl3 or CONH3 whole 5 Cl, Cl2 and CONH3 whole 4 Cl2 Cl behave as 1:3, 1:2 and 1:1 electrolytes respectively. It means when CONH3 whole 6 Cl3 is dissolved in water, it dissociates in 1 positive ion and 3 negative ions. When CONH3 whole 5 Cl, Cl2 is dissolved in water, it dissociates in 1 positive ion and 2 negative ions. And when CONH3 whole 4 Cl2 Cl is dissolved in water, it dissociates in 1 positive ion and 1 negative ion. A similar situation exists for PT NH3 whole 4 Cl2 Cl2, which behaves as a 1:2 electrolyte and has only half of the chloride ions precipitated when silver is added to a solution of the complex. Actually, the 2 chloride ions which are bounded by primary valency only get precipitated with silver as silver chloride. This was the experimental interpretation of Werner's theory, which we will continue in our next lecture also. So, up to now you have come to know that it is very important to learn the chemistry of complexes, as the solutions of complexes also affect the conductance power of the solutions. In the end of this lecture, let us revise what we have discussed today. We learned about difference between a double salt and a complex, coordinate bond, definition of coordination compounds or complexes, Werner's coordination theory, and interpretation of experimental data by Werner. This interpretation of experimental data we will continue in our next lecture, and we will also define some basic terms like effective atomic number, coordination entity, central atom, and ligands.